So we started with the implementation of binary search tree, and in the last session we have seen how to implement the create function for a binary search tree, or how to insert a node into a binary search tree. So we have taken this example which we have solved, and which we have created using the insert function, and one by one we kept on inserting a node as per the given data into the binary search tree. And this is how the implementation was visualized. First, data was 8, and since there was nothing in the binary search tree, so the 8 become the root of the binary search tree with its left and right pointers pointing to null. Then came 3, and 3 is less than 8, so it goes to the left side of 8 and becomes a left child. Then came 10. 10 is greater than 8, so it becomes a right child of 8, and it goes to the right side of 8. So this way, the entire tree has been created, and finally, we get the tree which is shown on this left side. Okay, this entire tree. Now we have seen the create function or the insert function for inserting a data, or you can say inserting a node into the binary search tree. And we have seen the recursive implementation of it, and we had a discussion on this. And then the next point to discuss, sorry, the next point to discuss is about traversing a binary search tree. Okay, so once we come to know whatever we are creating, or whatever nodes we are inserting into the binary search tree, those nodes are properly getting inserted or not. For that, we need to traverse a tree, and then only we come to know, yes, the tree has been properly created. Otherwise, we are just inserting the nodes into the binary search tree. Yet, we do not know whether whether that tree is being properly created or not. Okay, so that we need to check, and that can be done with the help of a traversing. So we need to traverse. We need to check while traversing that whether the tree has been properly created or not. Okay. So the first traversal technique is called in-order traversal. Then we have pre-order traversal, then we have post-order traversal. Okay. So let us see what is in-order traversal. In-order traversal of a binary search tree. Now, these traversal techniques are applicable to a binary tree also. So it is a binary tree and binary search tree both. So the same data we are going to consider, and so we have the same binary search tree with us. And when we talk about in order traversal, so I said you that there is a relation between your in order, pre-order, post-order, and infix, prefix, and postfix. So what do we used to have in infix? In infix, the operator is used to be there in between the operands. Okay, means the operation which you are going to perform, which is defined by the operator, that operator is placed or fixed in between the operands. That is in fix. Likewise, exactly in order, what happens? Yeah, we have three things. We have root, we have left child, and we have right child. Okay. Now we know that the entire tree is formed using this concept only. You have one node which is designated as a root node. Then the remaining nodes are partitioned into n greater than or equals to 0 disjoint sets, and each of this set is a tree in turn. So that is important, that each of this set is a tree. Okay, so that recursive definition uh, takes us to a point where we can think that basically you have a root node, then you have a left subtree, then you have a right subtree. Okay, the left subtree root, the root of the left subtree is your left child of the main root. Okay, just a minute, please. Yes. So in order, what we are going to do, whether it is in order, pre-order, post-order, you always need to remember that we display the content of a root node. I repeat, we display the content of a root node. Okay. Again, I repeat, we display the content of a root node. Okay. When I say we display the content of a root node, I mean to say we process the content of a root node. So whatever operation you are going to perform, whether you are displaying the data, whether you are adding up the data, or you are performing any kind of operation. So basically, we say that we visit a node. I repeat, we say that we visit a node. Okay. Now that visit can be done to display the content, to add up the content, to sort the content, and so on. So you can perform n number of operations. But in general, all these operations are generalized in a term called visit. So we say that we visit a node. I repeat, we say that we visit a node. So basically, whether it's in order, it is pre-order or it is post-order. When I say we visit a node, so basically we visit the root node, or we process the root node, or we display the root node. Okay, so it means that root node is important for us. Okay, where the root node is coming, we have three things. I repeat: left, root, right, left, root, right, left child, root node, and right child. Okay, so the position of this root node which we are going to visit, which we are going to display, the position of this root node is basically going to define the traversal technique. The position of the root node is going to define the traversal technique. Okay, it can be in order depending upon the position of the root, it can be pre-order depending upon the position of a root, and it can be post-order depending upon the position of a root. For your kind information, let me revise you that in infix, prefix, and postfix, the position of the operator was important. The position of the operator used to define what kind of expression is this. If the operator is positioned in between the operands, then it is infix. If the operator is positioned before the operands, then it is prefix. If the operator is positioned after the operands, then it is postfix. Exactly like that only, if we position the root node before left and right, then it is pre-order. If we position the root node between left and right, then it is in order. And if we position the root node after left and right, then it is post order. Okay. So what is in order traversal? This is in order traversal. Left, root, right. Okay. So first we go to left, then we go to root, and then we go to right. Okay. Left, root, right. When I say left, so it is left child. Root is a root, right is a right child. Okay. And then we have a shortcut for this. And generally we write it like this. L stand for left, R O stand for root, and then R stand for right. Okay. L stand for left, R O stand for root, and then R stand for right. So my shortcut for in order traversal is L R O R. L R O R. Or I can say left, root, right. So root is position in between left and right. That's why it is in order traversal. Root is root is positioned in between left and right, and that's why it is called in order traversal. Okay. Now let us see that when we follow the in order traversal for this given example binary search tree, so what is the outcome or what is the result? We start with the root node, obviously. So we'll be starting with the root of a binary search tree. And what we need to do, we need to first go to the left. Okay. So first I would go to the left. So I come to 3. Is there anything on the left of 3? Yes, there is something on the left of 3. So we go to left again. So first left means you need to complete the entire left. Only after completing the entire left, then you need to move to root, and then you need to jump to right. Okay. So I keep on moving and I come to this 1. When I come to 1, so what I see that on the left of 1 there is nothing. Or I can say there is a null. On the left side of 1, there is null. Since there is a null on the left side of 1, I say that the left has been exhausted, or there is nothing on the left hand side. So my left is done. When my left is done, I come up and this is my root. And now since this is my root, when I come up, when I come back from my traversing, so I am coming back to root. The moment I come back to root, now I need to visit this. Okay, I need to visit this. And in this case, our visit is basically displaying the content. So we will display the content, that is 1. Sorry. So we display 1. Okay, so 1 is displayed, and let me make it square. So this is done, I mean to say. This has been visited, this has been traversed, you can say. So 1 has been visited. Now we need to go to the right of 1 because root is done. The moment you visit a root, then you need to go to right. So is there anything on the right of 1? There is nothing. It is null. So since there is nothing, so again come back. Okay. So when we come back from 1, so we get back to 3. When you get back to 3, so the left of 3 has been visited. I repeat, the left subtree of 3 has been visited. There is nothing on the left subtree. There is nothing in the left subtree of 3 which is not visited. Okay. So what we do now, we make 3 as a root, and now we need to visit 3. The moment we visit 3, so we display the content of 3. So 3 is displayed. Okay. So first 1 is displayed, and then 3 is displayed. The moment 3 is displayed, root has been displayed. So when root has been displayed, so we need to jump to right. So we need to go to the right of root. So we come to the right of root, and to the right of this root, that is 3, we have 6. When we come to 6, so again we need to go to left. First, you need to completely visit the left subtree, then only you can go to its root, and then only you can go to its right subtree. Okay. So go to the left of 6. On the left of 6, you have 4. Then go to the left of 4. What do you have? You have nothing. So there is a null on the left of 4. Now, since there is a null on the left of 4, so the left subtree of 4 has been done, I can say. So I come back and I visit 4. Okay, because 4 is the root of this left subtree of 4, which does not have anything. So I visit 4, so 4 is displayed. Then I come back. And when I come back, so I reach to 6. When I reach to 6, the left subtree of 6 has been visited, and 6 is the root now. So now I will be visiting 6. So I visit 6. After visiting this 6, which is a root for this subtree, I go to the right of this 6. Okay. So I come to 7. Then I go to the left of 7. There is nothing on the left of 7. It is null. So I come back. When I come back, so this 7 is the root of this null. So what I do, I display 7 or I visit 7. Then I go to the right of 7. I don't have anything on the right of 7. Then I come back. Okay. When I come back, then I come back to 6 from 7. Then I come back to 3 from 6. And then I come back to 8 from 3. When we are coming back to 8 from 3, what we can see easily that The left subtree of 8 has been completely visited. Please see here carefully. The left subtree of 8, the main root node, has been completely visited. Now, since the left subtree has been completely visited, and when you come back to this 8, which is a root now, so we need to display 8 or we need to visit 8. Okay, so now we'll be visiting 8. So let me make it square. Then I go to the right of 8, which is 10. I go to its left, which is null. Then I come back. This 10 is the root of this null. So I need to display this 10 or I need to visit 10. I visit 10. Then I go to the right of 10. I come to 14. Then I go to the left of 14. I come to 13. Then I go to the left of 13, which is null. Okay. Then I come back and I come back to 13. Now I display 13 or I visit 13. Then I go to the right of 13, which is null. So I do not have anything. I come back. Then from 13, I come back to its root, which is 14. And I display 14 now. Okay. After displaying 14, I go to its right. There is nothing on the right. So I come back to 14. And when I come back to 14, I come back to 10, which has been already visited. And then I come back to 8, which has been already visited. And this is the main root node of the entire binary search tree. So now I say that my tree has been completely traversed. All the nodes of my tree have been visited. Okay, because now I have visited the right subtree of my tree also. So we have visited the left subtree, then we have visited the root, and then finally we have visited the right subtree. Okay, so this is how the in-order traversal would be done. And when I see the output, so I get this output. So first one would be displayed, and then we come back, 3 would be displayed, then we go to the right of this, then we go to the left, then 4 would be displayed, then 6 would be displayed, then 7 would be displayed, then we come to 8, 8 is displayed, then we come to 10, we go to its left, there is nothing, we come back, we display 10, then we go to its right, then we go to its left, 13 is there, we display 13, then we come back because there is nothing on the right of 13. We come back to 14 and 14 is displayed. And this is how all the nodes of my binary search tree have been visited. Okay. And this is finally the output for in-order traversal. The best thing about in-order traversal is that when you visit the binary search tree, I repeat, when you visit a binary search tree in an in-order traversal, it will give you a sorted list. I repeat, when you visit the binary search tree in order traversal, so it will always give you the sorted list. Okay. So whatever is the numbers in the binary search tree, if you see the in order traversal, you will be always get the sorted list in the ascending order. So you have 1, 3, 4, 6, 7, 8, 10, 13, 14. And the data was what? The data was this. 8, 3, 10, 1, 14, 6, 7, 13, 4. Okay. So the data was unsorted. Then we created a binary search tree of the given data. We traveled the binary search tree in order traversal and we get a sorted list. Okay. So this is in order traversal. If you practice it once or twice, you will definitely understand how it works. And then if it is a number, and when you give the number in the ascending order, you have the in order traversal. It is as simple as that. Any query into this, or we can shift to the next traversal technique. Before getting into the next reversal technique, let's see the implementation. This is a recursive implementation, which is quite small, straightforward, and simple. It's a little difficult to understand because it is recursion. To understand it, you need to have a good knowledge of recursion. You need to understand how the stack works, how the function call works, and so on. So in order traversal, a function is in order. I am passing the root of the binary search tree, which I want to visit in an in order traversal. And I will keep on calling my function recursively. Recursion is a conditional call to itself. I repeat, recursion is a conditional call to itself. So I have a condition. So if my given root is not null, if the given root is not null, then again same in order, but now my left child is the root. So I first completely traverse the left subtree. So in order R of left. When I completely traverse the left subtree and there is nothing, for example, if there is null, then I would be displaying the content. Okay. So printf slash n percentage d R of data or data of R. And then once I display the root, then I go to the right subtree in order R of right, calling the same function. Okay. So the function is small and simple. If my root is not null, I would keep on moving to the left side. And when it is null, I would display the data. Then I would keep on moving to the right side. Okay. So this is nothing, but I can say, but if I write here, left, root, right, in order to. So first I need to complete the left subtree, and that's why R of left in order, R of left in order, R of left, and so on. It will keep on doing till the condition is true. The moment the condition is false, it reaches null. If you see here, so when we started from 8, when we started from this 8, we go to the left of 8. So we go to 3. We do not display 3. We go to the left of 3. Then we go to the left of 1. Now since there is a null, so we come back and display 1. This is important. So till we reach the null, we keep on moving left. And that is the perfect condition for it. Okay. If R is not null, keep on moving to the left hand side in order R of left, in order R of left. The moment it is null, it is returned, and then we display the content R of data, and then we move to the right subchild, okay, or right subtree. So in order R of right. So this is my left, this is my root, and this is my right. Okay. So if I write here, so this is my L, this is my RO, and this is my R. L, R, O, R. Okay. So this is our in order traversal. Pre-order, it is pre. So same style, just like in order. The only thing is that pre means root will be positioned before left and right. So your printf is before left and right. That's all. The function names are pre-order. Okay. Likewise for post order. Your printing is after. So my pre-order, root, left, right, and inside this, if not null, I say root, left, and then right. For post order, it is left, right, and then root. So it is left, it is right, and then it is root. When I say root, so basically it is visiting a node. And in this case, we are visiting a node to display the content. That's why a printf. When I say right, so we are moving into the right subtree. So it is the same function call, but for R of right. When I say left, L, so it is the same function call, but for left subtree. So R of left. Exactly in the same way in other functions. Okay. So we have seen this as a in order traversal. Now let me execute our code. That would be better way to understand it. Okay, it got compiled. Okay, now it got compiled. And I have my application. I will keep on inserting the data, and let me go for the same example. And our data is this 8, 3, 10, 14, sorry, 1, 14, and so on. So the first data is 8. This is my first node. I go for one more insertion. Second is 3. I go for one more insertion. Then it is 10. I go for one more insertion. It is 1. I go for one more insertion. After 1, it is 14. I go for one more insertion. After 14, it is 6. I go for one more insertion. After 6, I have 7. And then after 7, I have 13 and then 4. 13 and then 4. Okay. So all nodes have been inserted into the binary search tree. And let's see when we go for the in order traversal, then what happens. So I go for the second option. And here I have the in order traversal. What we have? 1, 3, 4, 6, 7, 8, 10, 13, 14. Ascending order. And that's what we got the output over here. Okay. In the ascending order. 1, 3, 4, 6, 7, 8, 10, 13, 14. Okay. And if I go for the pre-order, sorry, third one. So we have this output. You cannot say that it is descending order or in any specific form, but it follows the logic of pre-order. That is root, left, right. First root is displayed, then the left child of that root is displayed, then the left, and so on. So 8, 3, 1, 6, 4, 7, 10, 14, 13. And if I go to post order, so my root would be displayed at the end. So 8 would come at the end, in short. So let me go for the fourth one, post order. Yes, you can see here 1, 4, 7, 6, 3, 13, 14, 10, and then finally 8. So one thing you need to keep in mind, only in order traversal gives you the sorted list in the ascending order. Pre-order and post-order do not give you any ordered list. They give you the list in the order of their logic. So pre-order is root, left, right, and post-order is left, right, root. So according to that logic only, you will be getting the output. So for example, if I go to the second one, pre-order traversal of binary search tree, same data, same tree, and as I said you, the logic is root, left, right. So what happens? First of all, the root would be displayed. So first of all, this root would be displayed. So the first number is 8. Then we go to its left. So we get 3. Then the 3 is the root. So again 3 is displayed. Then we go to its left. Then 1 is the root. So 1 is displayed. Okay. Then there is nothing on the left side of 1. Then we come back. We go to right. There is nothing. We come back to 3. And then we go to its right. And we display 6. Because this is the root of this subtree. Then we go to its left. We come to 4. And then we display 4. Then we go to its left, there is nothing. Then we go to its right, there is nothing. Then we come back to 4. We come back to 6. Then we come to 7, and 7 is displayed. Then we go to left of 7, there is nothing. Then we go to right of 7, there is nothing. We come back to 7, then we come back to 6. We come back to 3. we come back to 8, then we come back to 10, and then 10 is the root, so 10 is now displayed. Then we go to its left, there is nothing, we come back, then we go to its right, then 14 is displayed because 14 is the root now. Then we go to its left, and then finally we display 13. So this is the reorder. 8, 3, 1, 6, 4, 7, 10, 14, 13. 8, 3, 1. So pre-order, third option. This is my pre-order. So that's what I was saying you. 8, 3, 1, then 6, then 4, then 7, then come here, then 10, then 14, then 13. Okay. So this is your reorder traversal. Root, left, then right. Root, left, then right. Root, left, right. Okay. Come back to this part, then we go to post order. Same example. For post order, the logic is left, right, and then root. L, R, R, O. L, R, R, O. Okay. And then this is post order. So root would be displayed at the end. So first we come to 8, we go to its left, we come to 3, we go to its left, we come to 1, then we go to its left, there is nothing. There is nothing on the left of 1. Then we come back to 1. We do not display 1 because root is at the end after right. So the left has been visited. Now we visit right. So there is nothing on the right also. So we come back and then we display 1. Okay. So the first node which is going to get displayed is 1. Then after 1, we come back to 3. We do not display 3. We go to its right because there is something on the right. Then we come to its left. Then we go to its left. There is nothing. We come to 4. We go to its right. There is nothing. Then we'll display 4. So after 1, we display 4. Then we come back to 6. Then we go to its right. Then we go to its left. There is nothing. We go to its right. Nothing. So we display 7. Then we come back to 6. Its left has been processed. Its right has been processed. So we display 6 now. So first 1 would be displayed, then 4 would be displayed, then 7 would be displayed, and then 6 would be displayed. Then we come back to 3. Its left has been processed. Its right has been processed. So now we display 3. Then we come back to 8. We go to its right, we go to its left, we go to its right, we go to its left, we go to its left, we go to its right. There's nothing. So now 13 is displayed. We come back to 14. We go to its right. There is nothing. So we display 14. We come back to 10. Its left has been processed. There is nothing on the left. Right has been processed. So now we display 10. Then we come back to 8. Its left subtree has been processed. Its right subtree has been processed. Now we display 8. Okay. So what is the sequence? The sequence is first your 1 is displayed, then 4 is displayed, then 7 is displayed, then 6 is displayed. So 1, 4, 7, 6, 3, like that. So let me show post order. So yes, 1, 4, 7, 6, then 3, then come here, then 13, then 14, then 10, and then 8. So that is your post order traversal. Okay. And likewise, you have the function for it. I will explain you pre-order, in-order, and post-order. Fine. Any query from your side? Let me stop the recording.